Hello my passionate friends, this video is about fluids. We will focus on mainly static fluids, not the moving ones, stationary ones. And we will talk about pressure in fluids, and in this context we're gonna apply fluid properties to gases as well, especially to air pressure and so on. We'll focus on two principles. One is the Pascal principle, one is the Archimedes principle, and we will learn how to solve problems involving those principles. First, I want to talk about what is density. This is a generally covered topic in high schools and middle schools. If I have an object, it could be fluid, gas, or even solid. Its density is named as rho here, another Greek letter, is divided by its mass. It's equal to its mass divided by its volume. That's it. And we all know what mass and volume are. Its SI unit for mass is kilogram, volume is meter cube, so the unit of density will be in SI units. Standard units will be kilogram per meter cube, and we will stick with standard units. Here are some densities given. It could be a density given where I have to find values of mass and volume, or vice versa. We will focus on fluids and gases here. And we already learned that a gas can be put in a container, and that container defines its volume. Particles will be freely moving around that container. Volume of a liquid is similar. Container defines the volume of a liquid, but the molecules are closer together. They are tied to each other with weaker bonds, so they impact each other, but they can still move around. So the volume of fluid can also be changed. One very important difference is we can compress gases, but we cannot compress fluids. So we can change the volume of a gas, but volume of a fluid will be staying the same. They take the shape of the container though. Pressure is defined as force divided by the area. Everything has a pressure. Gases, we talked about gas pressure a lot already, can be calculated using this as well. We will focus on pressure of fluids here. If we assume a force applied to a certain area in a portion of fluids, we can find its pressure using that force divided by the area. We shortly touched base on this before too. So force divided by the area, that's pressure. SI unit of force is Newton. Area is meter squared. SI unit of pressures would be Newton per meter squared, and we call it Pascal. We can calculate the pressure of we can measure the pressure of a fluid using a simple device with a spring here. We put it inside the fluid. Fluid will apply a force here. We can know this area, calculate it, and then force applied by the fluid will be equal to the force applied by the spring. We can use that to calculate force and find a pressure as force divided by the area. There are devices doing that for us, and we can measure the pressure of a fluid using them. One important thing here is the pressure of a fluid is carried at every direction. So if I'm measuring the pressure of a fluid at this level, let's say, no matter if I put my device upward like this, sideways, or even upside down, at the same level, this applied force I'm going to measure will be the same, so I'm going to measure the same pressure. This is a very important fact here. So the pressure of a liquid at the same level is always the same. We can calculate again pressure using force divided by the area. For example, if we take a column of a fluid and look at what is the pressure at this point, we can calculate by using the forces. First of all, there is a force applied upward here and downward. At this point, we will have weight of that fluid downward. Additionally, air outside will apply a pressure, and that will bring a force. This will be the force of air. So pressure of air times area would be the force of air. And we can write down an equilibrium for that point. So upward forces, that would be the total pressure at that point times the area, is equal to downward forces, mg, plus the force by the atmosphere. That would be pressure of the atmosphere times the area. Again, this comes about by the fact that F air here would be pressure of the air. We always will call the pressure of the air or air pressure as P0 at this context, divided by the area it applies. The area I'm talking about will be the area of interest here. The bottom area of this column, fluid column I'm considering. Then by dividing everybody by area, I can just solve for the pressures. And area cancels here, cancels there. I'm going to get down to this equation. And this will come out of mg divided by A. P0 is there. How does that happen? We learned that the density is equal to mass divided by the volume. So mass can be replaced by density times the volume. And volume would be area times the height of this column we're talking about. The bottom area times the height is the area, the volume of a cylinder. So once I input this here as mass, I'm going to get down to this equation here. So I'm going to have rho times A times D divided by A. Don't forget G divided by A plus P0. That's equal to P. I'll carry it here. It takes me to this equation. What I'm trying to get at here is we're going to go ahead and use this equation. But I want you folks to know that that comes from the simple idea of force divided by the area is equal to pressure. That comes from the idea. So this guy always applies for fluids, for solids, for gases, and so on. This is a total pressure we experience at this point when the air pressure added. There's a terminology here I want you folks to be aware of. This is often called absolute pressure or actual pressure. If I'm looking for what is the pressure here, of course, if my container is open to air, I should add the air pressure as well. But there is also a name in here called gauge pressure. You might not be aware of that idea. I just want to tell you what it is. Gauge pressure is simply the pressure of the fluid only. So in this context, it will be this guy here. Or if I know the absolute pressure P, I can find the gauge pressure by just taking the difference from this equation, right? I'm solving for this. So this guy here is the P gauge. Once you hear about it in the questions, it's also included in your lab this week. That's what it is, simply. So, bottom line, gauge pressure is equal to total pressures or absolute pressure subtracted the atmospheric pressure. So absolute minus atmospheric. Atmospheric pressure we always call P0 in this context again. This page is talking about atmospheric pressure, how we can assume atmosphere is a liquid, and if we look at the column of an atmosphere, its pressure will be related to its density and the height. The density of the air decreases as we go higher and higher, which is why we know that if we go to highly elevated mountains, atmospheric pressure is very low, and the closer to sea level, it's very high. We mainly sea level. We'll talk about the pressure of atmosphere at sea level. That's called actually 1 atmosphere. So P0 is equal to 1 atmosphere at sea level. Local winds and weather also affects the air pressure, and air pressure also affects local winds and weather. Always we have winds from high to low pressure and so on. Atmospheric pressure can also be calculated using rho gh. So if, for example, at some certain mountain or certain place I'm considering a column of air, I measure its density and I look at its height. Overall in this region I can calculate the pressure of atmosphere using rho gh. Density, rho is density again, g is our dear friend, gravitational acceleration, and h is the height of the column. Notice here that for the height of the column for water we call it d, but it's simply the equivalent equation. H or d is the height. We use barometers to measure the atmospheric pressure actually, and for that what we do is we take a container and put some liquid in it, and we put it inside another larger container upside down like you see in here, and we let the fluid flow out because we know there is air pressure out here. When I put my container in, there will be a fluid pressure coming from here, air pressure out here, and the fluid will come out until the pressures at the same level are equal. So this is a very important fact here. Pressure of a liquid is equal at same horizontal level. We are considering air to be a liquid here as well. So out here I have P0. Inside here I have P liquid. So I can use this to calculate what is the air pressure here. The device called barometer does that for us. That's the working principle behind barometers, and they measure air pressure for us. We quite often use atmosphere for air pressure, and conversion will be 1 atmosphere is equal to 101.3 kilopascal or 101,300 Pascal, because 1 kilopascal is equal to 1,000 Pascal, 100,000 Pascal. Other units used, we mentioned psi before, pounds per square inch used in the United States, engineering industry, and we can convert to kilopascal, psi to kilopascal using this conversion factor. Inches of mercury is also used. Barometers generally use mercury because the height will be otherwise too high if the density of the liquid is lower. So we use a high density liquid, which is mercury. And we measure also in millimeters mercury. Millimeter is Hg, and 1 millimeter mercury is 133 Pascal. So we can use all these to do conversions. I'm going to mainly focus on atmosphere and Pascal, but if you see other values in questions, here are the conversions, and we know how to do conversions. A submarine cruises at a depth of 300 meters. What is the pressure at this depth? Give an answer in both pascals and atmosphere. A simple question here involving the pressure of fluids. We'll get to this a bit later, but the working principle behind a submarine is that it takes water in, its density increases, it sinks, and then it gives water out and it starts floating. But let's assume we are in the water here, and the depth, I'll call this H, 300 meters. And there's outside here, so there is also atmospheric pressure. Questions should have actually specified, but we will assume here P0 is 1 atmosphere because the submarine would be at the sea level, of course, right? So sea level, that's the pressure of the atmosphere, 1 atmosphere. And we will convert this to Pascal using this conversion. So 1 atmosphere, 101.3 kilopascal, or 101,300 Pascal. What else? Density of the seawater Let's call this rho C, 1030 kilogram per meter cube. We will need all these to solve for this problem. I'm just checking my values here. So all good. What is the pressure down here at 300 meters? Will be this pressure plus the pressure of the water, right? Not R, P of the water. So I'm going to call it P water. This thing alone would be the gauge pressure. Remember, the pressure of fluid alone, it will be rho G times the height, or D, H or D. I call it H in this case. And rho is, the fluid is water now, so rho will be water, seawater. That's called gauge pressure. Again, just to keep the terminology here. But we're looking for the total pressure, so we'll look at P0 plus rho GH, and that's all. I'm going to put P0, the atmospheric pressure, as Pascal, 101, 300 Pascal, because if I take all these values, the density of the sea, G and H, height of the water here, in SI units, I'm going to find Pascal. So this plus density of the seawater, 1030 kilogram per meter cube, times our dear G, 9.8 meters per second squared, times the height, 300 meters, will give us a total pressure of, let's see, 3,129,500 Pascal. This is a really large number. Maybe I'm going to write it in terms of scientific format. I'm going to move back 1, 2, 3, 4, 5, 6 step, right? 3.13, I would round this to 13 here. It will be 3.129 times 10 to 6 Pascal. Or quite often we have a large pressures, we convert them to kilopascal by dividing by 1,000, so 3,129.5 kilopascal. Then I can convert this to atmosphere. So 1 atmosphere, here we said, right, 1 atmosphere is equal to 101.3 kilopascal. You can convert from Pascal or from kilopascal. All should work. So all I have to do is multiply this by 1 atmosphere divided by 101.3 kilopascal, a regular conversion way. Simply dividing this guy by 101.3 will be converting it to atmosphere. And that will be 3.89 atmosphere. No, sorry, 30.89 atmosphere. Rounding up, we can say about 30.931 atmosphere. And here, as I added the conversion table here for us to check again. Go ahead to convert this to millimeter per mercury, or American unit, SI unit, pounds per square inch. Idea is the same. All right. Here's the question involving this idea again. At the same horizontal level, pressures are the same. Here I have at this top level, I only have atmospheric pressure. They are equal. Makes sense, right? If I look at here, this could be a little bit challenging to wrap our head around. At point 1, I'm showing here 2 and 3 pressures are all equal. So P1 is equal to P2 is equal to P3 here. P1 and P3, I can see I have P0 plus this height, right? I add rho GD here, the same there. But P2 a bit confusing. Why P2 is equal to all of those? It's because the pressure of a fluid is carried in all directions. If I have a pressure here, it's carried in there, in there, in there. So at the same level, at the same horizontal level, it will always be equal. This is a very important principle. Pressures are equal. The same here. P1 is equal to P2, same horizontal level. Doesn't matter if I have a more liquid, wider container here than this one. Still it will be the same. Here I would also have P0 out here, both sides, and so on. This question is involving this. We have iceberg and sea. How do you compare the pressures at 1 and 2? P1 and P2. They are equal because they are at the same level from the sea surface. It doesn't matter if I have this iceberg here and it looks like I have less. Again, all the pressure from here is carried to there and there, so they will be the same. And this idea of pressures being equal at the same level is widely used in industry. One very common use is lifting objects. And how we use it as hydraulic lift, as we call it. How we use it as we apply a force on one side of a fluid and lift a very heavy object with a very small force. Let me retry this. I did a messy job here. I'm going to draw a line maybe. Oops. Let me carry that a little bit. Here we go. All right. That's better. So at the same level, we will have the same pressure. We will have a pressure here. I'm going to call this P1. This pressure will be carried everywhere, right? And over here, I'm going to have pushing this guy up with that pressure. And from top, I have the pressure of the car. I'm going to call this P2. At the same level, pressures are the same, tells me that P1 is equal to P2. Again, the reason they are equal because the pressures are carried everywhere. They have to be at the same level though. Then I apply a force here. I have an area there, and I apply a force here. The force applied for the right side would be let me use black here. The weight of the car. I'm just showing it here. mg, right? It pushes down, and by making that area larger, so here I have mg pushing down, I have F pushing here on the left to lift that car, and area 1, as you see, this area here is significantly smaller than area 2. By maintaining that and using the fact that P1 is equal to P2, I can apply a small force here and lift up a very large car, which has a very large weight applied to the right side, which will be the force applied here. This would be my F2. So pressure on the left, force 1 over area 1, applies a pressure. That pressure is carried to the right by the liquid, and on the right, pressure 2, F2 over A2, then is equal to that. This is called Pascal's principle, and all the hydraulic lifts uses this principle. Notice here that F1 is inversely proportional to A2. So if I increase A2, I can apply less and less force to lift that car. But solving problems involving that is a very simple idea. I will say the pressures are equal at the same level. So pressure on the left is equal to pressure on the right. F1 over A1 is equal to F2 over A2. And we will solve for unknowns. Let's apply this to a problem. Here we have 10 kilogram on the left and it's lifting another mass on the right. Of course, the mass on the right is larger because area is larger. But pressure 1 is equal to, this should be pressure 1, is equal to pressure 2. Pascal's principle helps us solve this problem. F1 will be M1 times G. That's the force applied here. And this 10 kilogram is our M1. And I don't know M2, but F2 would be M2G, I know. The question says a 10 kilogram load of small piston lifts a load of M2 kilogram. If area 2 is 50 times larger than the area 1, so if this is A and this is 50A, what is mass 2? So again, Pascal's principle tells me at the same level pressures are the same. F1 over A1 is equal to F2 over A2. And I'm going to put in the areas now. F1 is M1G, A1 is A, F2 is M2G, and A2 is 50A. And solve for M2 knowing M1. M2 will be 50 times M1. So the larger the area, the larger the weight I can lift on here, simply. So M1 was 10 kilogram, input that in. I can lift up a 500 kilogram mass with applying this much of mass on the left side. So that's Pascal's principle. So over this part, overall what I want you folks to know is that the pressure of a fluid alone, P fluid, is calculated density of the fluid times gravitational acceleration times height of the fluid. Alright, density times gravitational acceleration times height. Simple. We talked about how this is related to force and so on, but this is overall what we want to know. If there is outside pressure, if the system is open to outside, like this figure you see here, we will have atmospheric pressure, we will add that, right? P atmosphere. And we call this P0 generally. Alright. If I add the P0 here, I call it absolute pressure. And I say total here, if there's atmospheric pressure, I add that. Time plus the P fluid. This is called absolute pressure, and this is called error here, spelling error. Oh, a lot of spelling. Absolute pressure and gauge pressure. All right. And another very important fact here is if I draw a line, and that line I can draw anywhere, folks. At the same horizontal level, pressures are equal. That's it. So I look at the pressure on the left, P left I can call it, or P1 let's say, and I look at the pressure on the right, P2, they are always equal. Notice here situation might change. If the right side is closed, I won't have P0 there then, I won't add it and so on. I can have the same fluid, different fluids. Here I have different fluids, right? If I call this density rho 1, I should call this rho 2 and so on. And apply the same idea. This idea is the very idea behind Pascal's principle. Apply a force here, lift something else on the right side. Idea is pressures are equal. Pressure I have on the left is equal to pressure I have on the right. P1 is equal to P2 because whatever pressure I apply here is carried to there by the liquid fluid I have there. One thing I have to be really careful about applying Pascal's principle, this type of situations could arise, but idea will stay as the same. Pressure on the left at the same level will be equal to pressure on the right. So notice here I have a little bit of liquid here as well. So I'm going to add F1 over A1 plus that liquid pressure that will be equal to pressure over here. Notice I can also add P0 to there, but it will be added on both sides if both sides are open to air pressure and they will cancel. Let's work on this last case here in equation y to apply this and see how it works. So this level, I'll say P1 is equal to P2. Then I'll calculate the P1 in total. I have P0, air pressure, plus F1 over A1, plus rho GH here, a little bit of fluid pressure, all added at this level, will be equal to P2, which is only F2 over A2. Sorry, not only that, plus P0. And from both sides, I can subtract P0. This guy will go away. And then I'll solve what is unknown. Tactic is always the same, folks. Think about what is happening. Draw an ugly picture of the situation. Draw your horizontal line and apply the fact that pressures are equal at that horizontal line. And then write down your pressures. Say pressure on the left is equal to pressure on the right and calculate your values. Here's another example. Water fills the tube. So this is water. What is the pressure at the top of the closed tube? Here, notice the tube is closed here. So we have P0 on the left, which is told us to be take as 1 atmosphere. But on the right, P0 is not impacting the top here because there is a rigid surface here and it applies a force against and cancel it. Alright, so we will say on the left is equal to pressure on the right. We are all calculating this pressure here. Pressure 1 is equal to pressure 2. Idea is the same. And pressure 2 is what is asked for us. So we'll say pressure 2 then is equal to P0 plus rho GH. What is my H? Is this distance here? This is 40. This is 100. So it will be 100 minus 40. 60 centimeters. 0.06 meters. Right? Divided by 100. P0 is 1 atmosphere. I'll go with Pascal here. 100,300 Pascal. 1 atmosphere. I'll input that. Density of water will take, if it's a regular water, not sea or salty water, 1,000 kilogram per meter cube. I'm going to input this guy, that guy, but I calculated H. And I'll find that pressure 2 on the right. So idea again is simple. Pressures at the same horizontal level are the same. And we'll find the pressure 2 as, when we put in all those, 180 Pascal, a very large number. Again, I'm going to convert to kilopascal by moving 3 steps back. Simply dividing by 1,000. That's how much kilopascal. I want you folks to go ahead and convert this to atmosphere by using 1 atmosphere is equal to 101.3 kilopascal, not kilogram. And you should find this to be P2 to be equal to about 1.06 atmosphere. All right, that's pressure of fluids. Again, we assume air pressure as the pressure of a fluid as well. We can calculate using rho GH, but it is often given as a value to us. The second idea we want to work on in this section is buoyancy, the force that is applied to objects if we put them into a fluid. We all know that if we put something into a fluid, something floats, something just sinks. We'll talk about that, why something floats and something would sink. And we all know that if something floats and we push it down, a floating object, we push it down, assume you're putting a wooden block in this water, it will float. If you push it down, you will definitely feel a force upward. And that's the buoyancy force applied to you, to the object you put in the water. Archimedes' principle tells us that a fluid exerts an upward force called buoyant force. And the magnitude of that buoyant force is equal to the weight of the fluid the object displaces. So when I put an object into a fluid, Fluids are incompressible. So if I put an object of this size, it will push the fluid around itself, make itself a space here, and this fluid will be pushed up a little bit. So it displaces a fluid. And the weight of that displaced fluid is the buoyant force. If we calculate it, we will find it to be the density of the fluid, volume that is displaced. So this yellow area I showed here would be what they call in this equation V fluid, Vf. I would like to just call this V displaced. That's not the whole volume of the fluid. It's whole volume of the fluid is this. It's just the amount of fluid that is displaced. That's the volume we're looking at. Now we can easily define that. If I am submerging something totally into the fluid, the volume of the thing, something I'm submerging, is equal to V displaced, right? Or if I'm submerging only a part of it, that's how much fluid will be displaced. So we will be able to define the volume of the fluid that is displaced easily. Now a quick question here. A heavy lead block and a light aluminum block of equal sizes are both submerged in water. When we say submerged, we mean all of their body is in the water, right? So we have the same size of a lead heavy and aluminum, but they are the same size, right? Which one is a aluminum? Upon which is the buoyant force greater? So buoyant force will be equal to density of the fluid. I'm going to call this V, volume of the displaced fluid, as V displaced to describe it better, times G. That's the weight of the displaced fluid. This is simply M displaced, mass of the displaced fluid, times G. And the mass of the displaced fluid is equal to density of the displaced fluid times the volume of the displaced fluid. We use here the fact that density is equal to mass divided by the volume. So this is simply weight of the displaced fluid. This is to convince you folks that it is the weight. So equal size means they have the same volumes, right? V1 is equal to V2. V lead is equal to V aluminum. When I put them and submerge them in the water, they both will displace the same amount of volume. And that tells me the buoyancy force will be the same as long as the displaced volumes are the same. No matter how heavy one is, it will be the same. How the heaviness changes the situation is that if I put them in here and let them sink, lead will sink faster because it has a larger mg pulling it down, right? That's for sure. M1G is not equal to M2G. And aluminum will sink slower. Alright, same size, same display fluid, same buoyant force. Two blocks, identical size again. One is made of lead, one is and sits in the bottom, one is made of wood and floats. Now we have a different situation, folks. So let's draw the picture here. We have two objects, same size. Let's assume they're also round size. Lead, one is lead, and when we put it in the water, it sinks totally down. So if its volume is V, volume of displaced fluid will be equal to that V. And the other is wood and it floats. Let's draw wood in black. It floats means that V displaced will be only part of the volume, not whole volume. So it will be displaced in less fluid. Now using F buoyancy, again raw fluid, volume of the displaced fluid times G tells me that if I show the buoyant forces on these two guys as F buoyant 1 and F buoyant 2, F buoyant 2 will be smaller than F buoyant 1. because it displaced less fluid. Upon which is the buoyant force greater than is upon lead. Because it submerged more amount of its volume, it displaced more fluid, and it is applied a larger buoyancy force. So that's the idea here. Here is another question. Legend has it that Archimedes was asked by King Hero of Syracuse to determine whether the crown was pure gold or had been adulterated with a less valuable metal by an unscrupulous goldsmith. Since he was asked to define if it's gold or not, and he was interested in the buoyancy, he used buoyancy to define that. How did he do it? What he did is to weight the crown in the air when weighted in the water, and use that to calculate the density of the crown and compare it to the density of the gold, and he found that it wasn't gold because its density was significantly smaller than density of the gold. So we will do this. We will look at a situation and give values to calculate that. It was this problem that led him to the principle that bears his name. According to this legend, again, he figured it out when he was taking a shower, and he ran outside without thinking that he was in the shower, yelling that I found it, I found it. I don't know if you have heard of this story. Anyways, in a modern version of this method, a crown weighing 8.3 newtons suspended underwater. So if I suspend this underwater, it will have a weight, right? Weight of the crown, mg. It will be applied a buoyancy force. And I'm going to read the tension here according to equilibrium. If this guy is hanging here, not moving, F up is equal to F down, equilibrium. Alright, and I know the weight. I weighted it outside, and it's equal to 8.3 Newton. Alright, suspended under the water with a string. The tension in the string is measured to be 7.81 Newton. Is the ground cold? Again, we're going to find the density of the crown and compare it to gold. Now, how can I find the density of the crown? Using its weight, I can find the mass of the crown, right? From here, I would say mass is equal to weight divided by G. And if I do that, I'm going to find a mass of 0.85, about 0.85 kilogram. Now, if I knew the volume of the crown right away, right, I would say the density of the crown is equal to mass of the crown divided by the volume of the crown, right? But I don't know that, and I'm going to use this idea here to figure that out. When I put the crown in the water, it will be displacing some amount of water, right? And that amount displaced, if the crown is totally submerged, is equal to V crown. So Archimedes thought, if I decide that, find the crown's volume, input it in here, I can find its density, which is what he did. Given values here, we will say F up is equal to F down and write down our forces. We have tension up, we have F buoyancy up, and we have mg down. So F buoyancy is equal to mg minus T, 8.9 Newton, not 9, 3 Newton. I don't know where 9 came from. Minus 7.81 Newton. And that should give me a value of about, a small value, should have it here somewhere. 0. Oh, I don't have it. don't have it here. I directly calculated, but let's find it. I believe it's about 0.00 something. Hide this guy here. Quickly do that. So 8.3 minus 7.81. 0.49. There we go. All right, 0.49. Let's go back to here. So that's the buoyancy force applied to the crown. Now we also know that buoyancy force is defined as the density of the fluid, displaced volume, times g. So since I'm looking for the displaced volume, I can find it by using buoyancy force divided by density of the fluid times g. I know g, gravitational acceleration. I found this guy. I can put it in here. And the density of the fluid would be the density of the water, 1000 kilogram per meter cube. Putting all those in, we found the volume of the displaced liquid, which is equal to volume of the crown, about 0.0005 meter cube, 4 zeros here. So that will be, moving backward here, 1, 2, 3, 4, 5. So if I move this 1, 2, 3, 4, 5, 6 steps, right? 3, 4, 5 steps, sorry. 5 times 10 to minus 5 meter cube, or you can leave it as this, not so bad. That's the volume displaced. That's equal to volume of the crown. So we got the volume of the crown. And we input it in here to solve for the density of the crown. Mass, we found at 0.85 kilogram. Volume is very small, but it makes sense in meter cube, right? It's a crown, small thing. And we will find the density of the crown to be 16,938.78 kilogram per meter cube. The given value was about 17,000, which is close enough. About 17,000, one more zero, kilogram per meter cube. What Archimedes found, it's significantly smaller than gold, so it is not gold. All right. If we have something floating in a fluid, it's an equilibrium. And what we know what equilibrium is. Up forces are equal to down forces. So F buoyancy is equal to weight. Okay? Or, as I like to call weight, as mg. This idea will always hold as long as something floats in a fluid. If I put something that will not want to float, for example, if this is a wooden block, it will float. If I have an iron block, if I put it in the same way as I put the wood in, I know it's not going to float. It will sink. Because it's large density, its mg will be larger than F buoyancy. And it will sink to the bottom. It will try to be in equilibrium, but it will never be in equilibrium. Still have F buoyancy here applied to it, but it will not be able to sink because it has a very large density. If something can float, it depends on how large density it has. We can relate them to the densities. And if we summarize this, we will find that something will float. Something will sink if its density is larger than the float. It will float if its density is smaller than the float. And it will be in what we call neutral equilibrium if its density is equal to float. This is a very rare case. We rarely see a fluid and density of a solid equal, but if we can find it, what happens is that Wherever we put this object, it will stay there and it will stay all of its volume submerged. So it's like a float in the system, still weight will be equal to buoyancy force. This question is very nice in testing this, looking at densities. If I put 3 blocks in water, that's how they become in equilibrium. Alright. All of these guys are in equilibrium, means ma times g is equal to buoyancy force applied to A. Okay. Same goes for B and C. mb times g is equal to buoyancy force applied to it by water, and so on. mc times g is equal to fbc. That's one thing. Other thing is, if I put something inside water and check if it flows or not, it will sink until the mg, the weight, is equal to buoyancy force. If its density is large, more portion of its volume will sink in. If its density is small, less portion of its volume will sink in. Now over here, let me call the densities rho A, rho B, rho G, rho C. And rho fluid will be rho water. Definitely all are floating, so all are smaller than the water's density. Density of A is smaller than density of water. Density of B is smaller than density of water. And density of C is smaller than density of water. Okay? All are in equilibrium, so the buoyancy forces are equal to mass at the weight of the objects as well. How can I decide who is more dense? Is I look at the portion of their volume sank. If more than half sank for A and less than half of the volume sank for B, density of A is larger than B. If you see here, about half volume sank for C, so C would be in the middle. Now the question is asking which is most dense. That's A. The most of the volume of A is sank, so it's the most dense. But I can even compare them. A would be the largest density, then comes C, half of it is sank. And less than half of B is sank, so that would be the smallest density. Alright, density smaller than the fluid, objects floats. Amount of portion of volume sank gives us idea of comparison of the density of the objects. Very important fact here. This question involves this idea. It's more involved, of course. It gives us an unknown liquid, so I'm going to call this density rho, and water. I'm going to call this rho water. And it says we have a block. Of course, block has a density. I'm going to call it, let me use yellow, doesn't look good here. So I'm going to call this rho block, okay? Rho blocks. Density of the fluid, unknown fluid, I'm going to call rho F. And the density of the water, rho W. You need to determine density of this fluid. You notice that a wooden block floats in this liquid with 4.6 centimeter of the side of the block is submerged. So this submerged part has height as 4.6 centimeter. Now we know that we're interested in submerged volume, but these areas would be the same. So if we call it area A, the submerged volume would be this height times the area. So here we displaced one, this skull will be HU times A, right? And if I put it in the water, it's 5.8 centimeter of it is sank. And area again is A. The volume would be height times the area for a cube. So the displaced volume in the second case, we displaced 2, would be HW times A. Alright, first of all, I can guess who is denser, the fluid or water, by looking at how much volume is sinking here. Rho block is the same. I'm comparing the fluids. The denser fluid will be pushing it more up. Less amount of volume will be sinking. So the fluid should be larger. And that will give me an assessment, like I should get a value of the volume of the fluid larger than density of the fluid larger than density of water. We know density of water is 1,000 kilogram per meter cube. So let's see if we're going to find this. No matter how the densities compare, for each case, the wood floats. There's mg down, and there's buoyancy force up. Let's call them F buoyancy 1 and F buoyancy 2. All right. They are floating, means they are in equilibrium. So equilibrium tells me forces up are equal to forces down. Look at forces down, always mg. So F buoyancy 1 is equal to mg, according to that. F buoyancy 2 is also equal to mg. That mg is the same block. That means the buoyancy forces are equal to each other. And using that, I can solve for the density of the object. How can I do it? The density of the, fluid that I don't know. F buoyancy 1 is equal to F buoyancy 2. Okay, 1, 2. F buoyancy 1 is the density of the fluid. We displaced 1 times G, and F buoyancy 2 is the density of the water, not volume. We displaced 2. Okay, this should be displaced 1. They are different. We displaced 2 times G. Now G's cancels here. And here's my V displaced 1. Here's my V displaced 2. Here we have a ratio. We can keep the H's as centimeters, but we are used to converting. So let's convert centimeters to meters. Divide by 100, 0.046 meters, 0.058 meters. And I'm going to solve for raw fluid. So from here, raw fluid is equal to raw water. I'm going to put let's leave it as displaced 2 over displaced 1. We displaced 1, right? Now I put in all the values. Density of the water. We displaced 1 as the height that sinks in the fluid. We call it HU times A. Divided by we displaced 2. Height that sinks in water times A. A is also cancels here. Input all these values. We will get the raw fluid from here, which should be 1260.87 kilogram per meter cube. Larger than water. That's what I was expecting, because before the block gets into equilibrium, before FB equals to mg, it's pushed up more, so it's less volume sink. That means that liquid is thicker and it's able to push the block up further until it gets into equilibrium. Buoyancy is used in submarines as shortly how the submarines work related to buoyancy of water, or how the boats work related to buoyancy of water, or Achimedes principle. For the boats, it could be confusing to think about how come we have a steel boat, very heavy, large density fluids in the smaller density water, is by making the volume as big as possible and given empty spaces in the boats. We can make them to displace more and more water. If they displace more and more water, buoyancy force applied to them increases, and finally they are able to float. We can also think of boat and as having an average density, and as we put like empty inside of it, make the volume larger. So we put air in, kind of its overall average density decreases by doing that, and we have a floating boat, heavy boat. Similar idea used in submarines. Submarines has an empty tank, and they take water into that tank, And when they have water, they sink because they have overall larger density. And then they let that out, water out, push it out with the pressure. Then they have air back in here. And when they do that, they have less density. So they rise up to the surface. Similar idea goes for air balloon, hot air balloons. They are hot air balloons because what we do is we heat the air inside the balloon. So the hot air is less dense than outside air here. Cool air here. And we have hot air there. Different colors needed here. So hot air, less dense. Cool air, more dense. Hot air's volume increases, becomes less dense. Also helps the balloon to displace more of the air. So we displaced increases. Density of the balloon, let's say overall, decreases. And what happens then? mg becomes, at some point, mg becomes less than the buoyancy force the air applies. Here we are considering air as a fluid, and we can apply Archimedes principle to the air as well. And the balloon floats. If we want it to come down, we let some air out, we make it colder, don't need it anymore, and then the balloon comes down. So applications of Archimedes principle are numerous. This is a similar question to the ones we solved before. We have ABC, all the same sizes, different masses though, same sizes. Displaced fluids will be the same, so F buoyancies will be the same. Density of the fluid, water, displaced volume, all the same because same size and all submerged, times G. So F buoyancy A is equal to F buoyancy B is equal to F buoyancy C. So they all have the same buoyant force. Now what difference mg makes, right? That should be a question coming to the mind. What difference mg makes? As mg gets larger, let's assume none of these are able to float in the water and they will all sink. All right, they will all sink. But this should be MA, MB, MCG. Let me redo those. So this is MAG. This is MBG, right? This is MGC, MCG. A and B are equal. Let's say all have the MG larger than FB. There could be different situations, but this is one situation you could have. They will be sinking, right? This guy will be sinking. This guy will be sinking. This guy will be sinking. Who will be sinking faster? The heavier ones, because it has larger mg. So this guy will be sinking faster than B. Sinking at the same rate. If you look at F net and apply F net is equal MA, up forces, down forces, right? Take up positive, down negative, they would be going down with an acceleration, or you can take down positive because that's the acceleration direction, right? And find those acceleration. A and C will be accelerating more than B because their mass, their weight is way more larger than FB. That would be the difference. But buoyancy force applied to all will still be the same because it's equal to density of the fluid, displaced volume, times G. That's a very important fact here. We'll solve some more problems here. I have two examples here. I want you folks to attempt, and I will post video solutions to them. I'll give you the ideas. I'll give you the numbers you should find. Please attempt them, then watch the videos. We have a hot air balloon here. I'm going to draw an ugly picture. All right. Hot air balloon. It has air inside it. And that volume of air is given to us, 2,500 meter cube. Assume that balloon is flying in Fort Collins, which is not important, Colorado, where density of the air is 1 kilogram per meter cube. So we are given density of the air. All right, that's what we are given. Hot air balloon has air in this volume of 2,500 meter cube, flying in Fort Collins, Colorado, where air is 1 kilogram per meter cube. A, what is the mass of the air it displaces? For that one, you'll use two ideas. You'll find a displaced volume, which will be equal to that volume, right? How much ever volume this air has, that's how much it will displace, push the other air around. And you will use the idea that density of the air is equal to mass of the air divided by that displaced volume to solve for mass. That's it. So you'll say simply mass of the air is equal to density of the air times displaced volume. And find the mass of the air. And it should be, well, this will be quite simple, 2,500 kilogram, because raw air is 1 kilogram per meter cube, and displaced air is equal to that. All right, I kind of solved it. B says if heated to maximum temperature, the air inside the balloon has a density of 80% of that of the surrounding air. Now, if I heat it, I'm going to call it rho in. The air inside is 80% of raw air. That means like 0.8 times the raw air. So this raw air is 1, right? So it will be 0.8 kilogram per meter cube. What happens then? Less dense, more dense? It will be going up, right? So this guy is displaced in an air. There will be a buoyancy applied to it, and there will be a, let's say, m total g down at everything inside this balloon and air and so on, m total. And it's asking us what is the mass of the air in the balloon. So you know the density of the air in the balloon. You know the volume of the air in the balloon. It's the air volume given initially, right? Find the mass of the air in the balloon. I'm gonna call it m air in balloon, m air, or let's call it m n, because we called this guy m air. You guys will find that. And then C tells you how much mass can the balloon lift. That would be the total mass. That would be the air in plus m extra g. Okay, that will be the weight down, F buoyancy up, and you want to lift that. For the lifting, F buoyancy should be equal to m total times g. Now, if buoyancy is raw fluid, right? Our fluid is air outside now, times displaced volume times g, right? And that should be equal to m total times g. Input m total, you'll find the air in mass here, put it. You're asked to find how much extra mass I can put in and lift with that balloon. And that m extra you will find should be 500 kilograms. All right. Again, apply this, work on it, solve. Watch the video if you're good, solved it, understood, found the numbers. You don't need to watch the video then. This idea is commonly used in sea animals, idea of buoyancy and floating. Normally, for example, the regular anatomy of a fish and its density, if we look at it, its density is about 1050 kilograms per meter cube, just like our overall average density of our body. So they should sink if they don't do anything. What they have is what is called swim bladder, and by increasing the volume of the swim bladder, they change their average density. Because it's mass divided by the volume, they can't change their mass, but they can just take some increase the volume of this bladder that has a gas in it, and if they increase that, they decrease the density and they float. If they want to go down, they decrease that volume. And manatees does something similar, except they do that in their lungs. So they increase and decrease the volume of their lungs to sink and float. They look fat, but they actually have only 7% fat. That's mainly what they have is muscles, and they use their muscles, of course, as well. They also very interestingly change the position of the air in their lungs, having more air and less density, or less air and more density as they dive and come back. Let me try to draw that here. For example, if they make less volume and more dense in the front, density increases. If volume decreases, they can dive easily, or they push air more to the back side and make less dense here. That's right, less dense, more dense, or vice versa. If they want to go up, they just make the front less dense, back more dense, so they can rise up easily. It's very interesting, skillful tactics they have. This question I also want to give you, I also have a video solution on, is about how fish change the size of their bladder to swim, sink and float. The question is asking us, we have a swim bladder deflated, so less volume. Mass of the fish is given as 9.5 kilogram. And its density with this volume deflated, maybe we'll call it V1. We don't know. But its density, rho 1, is 1050 kilogram per meter cube. So simply using rho is equal to mass divided by volume, you can find what is that volume 1, right? Mass over V1, rho 1. It is swimming near the surface of the ocean. What volume of gas must the fish have in its swim bladder to achieve neutral buoyancy? Neutral buoyancy is when the density of the fish is equal to density of the seawater, which is 1030 kilogram per meter cube. So what you will do, mass doesn't change, right? It's 9.5 kilogram. You'll find another volume where the density will be 1030 kilogram per meter cube. So you find that volume 2. You already found volume 1 here. So these are all bladders added, right? This is with deflated bladder. And then you increase the volume a little bit by inflating your bladder. This is with inflated bladder. Then if you look at the difference, V2 minus V1, this should be V1 here. All right. You will find the V bladder, how much extra V bladder you added, right? V bladder added later. That's the idea here, and that should be about 0.00, very small, of course, 0.17 meter cube. Again, work on it, find it. You understood, you don't have to watch the video. You are lost watching additional video on that. I'll see you in class.